take their seats?
Yeah, she was there. Yes, yeah. Yeah, and so you were there. Yes, yeah. And the baby came. Oh my gosh, that's great. Just for the day. Yeah. I know, right?
All right, well, I have to say that April is kind of my favorite time of the year in the department because of the parade of graduating PhD students and the very nice colloquy that they present. And today it's my turn to be the introducer, which is a particular pleasure. So I'm very happy to be introducing Lehman Garrison today. Lehman's been a wonderful student here over the past 6 years and has been a really essential part of my group's sort of irregular quest to try to adopt or try to create the world's fastest cosmological n-body code. And I think very largely through Lehman's efforts we've actually succeeded. So he'll be here to tell you today about Abacus. Lehman came to us from Princeton and has really been just a very insightful collaborator on a very wide range of topics that we've had to encounter in doing this code. We've really been trying to challenge a lot of the underlying bases of how to do these kinds of calculations and also building our own custom hardware to do it. So I think we'll be hearing today about really an end-to-end view of how to build a very highly optimized computer code and computer ecosystem to go along with it. So without further ado, turn it over to Lehman.
Okay. Thank you, Daniel. Yeah, it's really a pleasure to be up here after 6 years and share what I've been working on. But first, I'm going to begin with some acknowledgements, as is tradition. I have to thank Daniel so much for being such an amazing advisor. I really feel like I stumbled across just the best grad school experience, amazing advisor, amazing project. And Daniel's patience and kindness and humor has really been essential to my grad school experience. And I also want to thank my committee, Lars, Cora, Chris, and Greg, especially Greg, who came up here from Columbia. And I'm looking forward to talking more about the thesis with them later. I want to thank some of my high school teachers and undergrad advisors who really set me on this path. The CFA administrators, Rob and Peg in particular, who do so much to insulate us from the higher bureaucracy of Harvard. Lisa Catella also has helped us order so many computer parts and then return them when they didn't work and then get them back and send it back and forth. We've bounced so many computer parts across the country, and thanks to Lisa. A lot of the work I'm going to be showing today was built on work that was started by the grad student Doug Ferrer. So I especially want to thank him, and also Mark Metchnick and Phil Pinto for starting the Abacus project back in Mark's PhD thesis. And now, these days, Nina is leading a lot of development on Abacus, and it's really been a pleasure to have someone of Nina's talent on the Abacus team. The whole Eisenstein group has been such a fantastic group to work in. I've had a great time. I especially want to thank the postdocs, Cameron and Svetlin, who helped me when I was first starting out and thought that BAO was pronounced bow and was a type of steamed bun. So hopefully I won't mix that up today. But yeah, the Eisenstein group has been so wonderfully supportive. I've also spent a lot of time with these guys, the Eisenstein Computer Cluster, Bob, Charlie, Ted, and the whole family. And you'll see a little bit more of them today. The CFA grad students and postdocs have just been the best and have made the last 6 years a blast. Here's us in Virginia Beach and Mexico and at Ashley and Alex's wedding. Yeah, so a lot of trips, a lot of fun, and maybe, Daniel, you realize now why my PhD took 6 years. There's, this is the time that we caught a mouse in a building and decided to let it outside. This is the time Brad and Dan got married on the roof. This is CFA Scotch Hour. I've had a blast. I want to thank Ben and our whole D&D group. Ben has brought together this great group of people, and the D&D, the game, is a lot of fun, but what's really fun is just hanging out with these people every week. I also want to thank some old friends from undergrad and new friends I've made, especially this guy, and Paulo. And I have to thank my family who set me on this path from a very early age. This is my brother graduating. This is me and my siblings, Haley and Skylar, my sister's wedding, me laughing at my brother as he falls off a tube. Now, I think at this point, a lot of astronomers would show themselves with a telescope as a child. I'm going to show me with a computer. So this is me at the first computer that my family bought. This is an old beige IBM PC. And this is the first computer that I built in high school. And I never thought that the skills I learned building computers in high school would be useful during a cosmology PhD. And yet they were. And somehow I think my family had a suspicion that these skills would be more useful than I thought, even if they didn't imagine it in particularly this form. So they gave me the means to pursue this passion, and I'm incredibly grateful. Okay, so I'm going to be telling you about large-scale structure cosmology today. So what is large-scale structure? If you take a census of the galaxies in the universe, you find that their locations are not random. Galaxies like to live near each other. Their distribution is clumpy. And so this famous image is the Hubble Ultra Deep Field, and it was taken by staring at a patch of seemingly empty sky about the size of a tenth of the full moon. And it's kind of hard to see the clumpiness that I'm talking about in this picture. You do better if you zoom out and also include the distances to each object. And if you make a map of that, then you end up with something like this. So this is the first slice of the CFA redshift survey conducted here. So you can imagine us, the observer, sitting here at this point. The distance to galaxies is labeled along this axis of the wedge. And this arc is positioned on the sky, along a strip of the sky. So each dot here is a galaxy. There's about 1,000 of them. And the thing to notice is that the distribution is not uniformly random. It's clumpy. You got this big coma cluster here, filaments, voids, sparse regions. So this was the very first systematic attempt to map the galaxies in the local universe, and it was immediately obvious that, wow, there is structure here. And this structure is what we call large-scale structure. Today's galaxy surveys include vastly larger regions. This is from SDSS, and it's actually only a local sample of SDSS galaxies, but even so, the CFA redshift survey that I showed in the previous slide was just a little blip in the center here. So the question becomes, why is the galaxy distribution filamentary and clumpy? So we think we have an answer for this, and that's gravitational instability. So the way this works is that 14 billion years ago, immediately after the Big Bang, there were no stars, there were no galaxies, there was only dark matter and gas with tiny density fluctuations imprinted left over from the Big Bang. Now, gravity attracts, so over time, regions of slightly more density gathered more mass in a runaway gravitational effect. Any initial irregularities in the density field were amplified. So on the left here, this is a timeline, this Big Bang. This is back when there were no stars or galaxies, just dark matter and gas, and eventually over cosmic time, 14 billion years, galaxies and stars emerge. So here's an animation that might help illustrate this process of gravitational instability. So initially, the distribution of matter in the universe is very smooth. You don't see much structure here. Color indicates density. So over time, regions of this simulation are going to become brighter and brighter, and you see these filaments start to form. At the intersection of filaments, you get these knots, these bright regions that we call halos, and these are where galaxies live. So this is an extremely zoomed out view. Galaxies are just little blips at the center of here. You couldn't even see them at this level of zoom out. So galaxies are the luminous tracers by which we can see this large-scale structure. And the overall framework in which we think about this structure forming is called lambda CDM. So we need two ingredients to make a simulation like this. Lambda refers to dark energy, and CDM refers to dark matter. So in cartoon form, it looks like this. We think about 25% of energy in the universe is in the form of dark matter. Dark matter is called dark because it does not interact with light in any way that we know. It interacts with gravity. We infer its existence by things like the rotation curves of galaxies and cluster velocity dispersions. Only 5% of matter is in the form of ordinary atoms, described by known physics. That's all the stuff that makes up us and the Earth and the sun and stars. About 70% of the universe is the energy densities in the form of dark energy, which is it appears to behave as a negative pressure that drives the accelerated expansion of space. So this model is extremely successful in producing simulations like the previous that match observations very well, but it's also kind of exotic. It invokes energy density in two components, dark matter and dark energy, that we don't have a full theory of. So really the shameful part of lambda CDM is that we don't know the lambda and we don't know the CDM. But we know how they behave. Lambda is a dark energy that appears to behave like Einstein's cosmological constant in general relativity. But we would like to know, is it? And why does it have the value it has? Similarly, CDM, cold dark matter, behaves like some unseen mass that's exerting gravity, and it seems to move around and cluster and behave like some small collisionless particle. But is it actually a small collisionless particle? And why does it have the density that it has? So these are some of the questions that we seek to answer when we study large-scale structure. So large-scale structure, which is the 3D distribution of galaxies in the universe, is a really sensitive probe of cosmology. So the way that we tackle this with computer simulations is we run simulations like the video you saw for a range of different cosmologies with different models for dark energy and dark matter. And then we compare the observations from galaxy surveys to the results of the simulations. We typically do so by quantifying the clustering in our simulations and in the sky with clustering statistics like the power spectrum and two-point correlation function, which I'll introduce as necessary. The simulation method that I'll be talking about today and that I've used during my thesis is called n-body, and that's because we sampled the initial density field of the universe, for which we have a predictive theory, with a set of n discrete particles, and then evolve that particle distribution under Newtonian self-gravity. So let me show some figures to break this down. So initially, after the Big Bang, all the density fluctuations are extremely tiny. And so the description of a field like this coming out of the Big Bang is analytically accessible. What's not accessible is the emergent distribution of galaxies and filaments and halos and so on. And that's why we need simulations. But starting from an analytic prediction of an initial density field, we can sample a set of particles from it. And that's what I'm showing on the right here. So you can see in this bright patch down here, we've got a bunch of particles clumped together, and I've colored the particles by their local density. We've got a void over here, which matches with this sparse region over here. And so now that we have a set of particles, we can compute how they would evolve under gravitational self-interaction. And that would look something like this, where we have an initial quasi-uniform distribution of particles, and over time, the particles start to clump together because gravity attracts, so any initial irregularities are amplified. We start to see a knot form here, or a clump that we call a halo. Another one up here, matter is draining out of voids and into these halos, and then we get two halos colliding. So that's how we use numerical simulations to go from prediction for the initial conditions to the late time clumpy galaxy-like distribution. So really but we don't do this with a few hundred particles like I showed before. We do this with billions of particles or hundreds of billions. So this is a very large swath of the universe, many hundreds of megaparsecs across. And what we're trying to do is run a simulation, analyze it as if it were data from the sky, and then check whether the cosmology that we got out of that analysis matches the cosmology that we put into the simulation. You need very large volumes to do this, to suppress the scatter in the answer that you infer, and also to show robustness against all these complications that arise in the analysis of galaxy surveys, such as redshift space distortions, where the velocities of galaxies distort their positions based on redshift, bias of tracers, and all sorts of higher order correlation functions and non-lambda CDM cosmologies where our analytic theories are not as robust. So Abacus is our attempt at making an n-body code that will do this. I do just want to share a really interesting historical note. So n-body simulations have been performed since 1941, actually, you could say. So Holmberg performed maybe what you would call the first n-body simulation, which was an analog tabletop setup in which he used light bulbs and photoreceptors to simulate gravity. So so he used 37 light bulbs for each galaxy that he was simulating and put photoreceptors at each. And in this model, the 1 on r squared Newtonian gravity is replaced by the 1 on r squared luminous flux. And he was actually able to reproduce some tidal tails in this galaxy interaction, which is pretty cool. With the emergence of computers that in the 1960s, direct integration became very popular, where you're brute force solving Newtonian gravity, then mesh methods, all sorts of clever hardware and algorithmic changes. And then in the supercomputer era, the push has been towards parallelization of n-body codes and now GPU acceleration. So GPUs are graphics processing units, and they're a way of accelerating the n-body computation. And it's what we use in Abacus. Now, the amazing thing is that in 2008, there actually were no GPU supercomputers. And now, if you look at the list of top supercomputers in the world, almost all of the top ones use GPUs for their performance. So Abacus is really riding this wave of incredible GPU growth. Okay, so now I think it's time for me to tell you about Abacus and what I've been working on. So Abacus is, like I've said, is our new code for performing massive cosmological n-body simulations. And it's based on an exact split of the near field and far field force, which I'll explain in the next few slides. But the result is that you don't need a supercomputer allocation to run massive n-body simulations. You just need enough storage to hold all the particles on disk, and then you can load them into memory as needed. The way we split the force also gives us extremely high accuracy of order 10 to the minus 5 fractional error, as opposed to the few percent level errors typical in mesh-based codes. Since we're only using one node often, one computer, to provide the raw horsepower, we use GPUs. We are testing a parallel implementation currently. Nina Maximova is doing a lot of that, and a lot of the work that I've listed down here in terms of further improvements to the code. So the classic challenge of n-body is that we're trying to compute Newtonian gravity, which naively requires you to compute the gravitational interaction from every particle on every other particle. So with n particles, that's an n squared operation. And this is computationally infeasible as you go to billions and hundreds of billions of particles. So nobody actually does that. Nobody tries to brute force the problem. So instead, what is done is you split the force into a near field and far field component. And that works as follows. So we're going to take our simulation and divide it up into a cubic domain made up of a set of cells, cubic cells, showing a 2D slice of it here. And we're going to ask, excuse me, what is the force on this green particle in the center cell. The force on this particle we're going to break up into two components, a near field and a far field. The near field is this dark region here, all the neighboring cells, and the far field is the shaded region, which we're going to compute using a multipole method. So the green particle in the neighbor cell will interact directly with 1 on r squared gravity, and this red particle in the shaded cell will be part of a set of multipoles that will interact with this particle. So this idea of splitting the force, as I said, is not totally new. In particle mesh methods, what you do is you take all your particles in the simulation, put their mass on a mesh, and then use that mesh to solve Poisson's equation in Fourier space. The regular structure of the mesh makes this very easy. The problem is that your force is not accurate on sub-cell levels. So you probably want to refine your force with some direct interaction, some direct pairwise interaction. But you can't naively do that because you've already included all mass in the simulation onto this mesh. So when you query the mesh for the force, you're including this particle that you wanted to do a direct pairwise interaction with. And this is shown schematically on the right-hand side, where the far field force is shown to leak to small separations. And thus, if you want to compute an exact 1 on r squared force, which is this solid line, you are going to be double counting if you do 1 on r squared here. So instead, you have to compute some compensated kernel. This is the dashed line in the near field. And this can be done with Green's function matching, but it's approximate and often slower than just doing 1 on r squared. So when we say Abacus has an exact split of the near field and far field force, we mean that Abacus's force kernel looks something like this, where the near field we're actually just doing 1 on r squared, and the far field is also 1 on r squared with a multipole method. Okay, so how does this multipole method work? We compute an approximation to the mass distribution, the multipole expansion of the particle set in every cell, and we apply a derivatives tensor, which is a property of the grid, to get an approximation of the potential in each cell, a given number of cells away. This derivatives tensor is called that because it's using the derivatives of the gravitational potential to get the acceleration. So this is a property of the mass distribution and is updated at every time step. This is a fixed, pre-computable property of the grid. And the nice thing is, because we're on a grid, everything is relative. I just chose this center cell here, and the derivatives are going to apply 2 cells over, but it's equally valid for the neighbor cell. So we can, in detail, convolve this derivatives tensor with this grid. So we convolve the derivatives tensor with the mesh of multipoles to get the Taylor series approximation in every cell from every other cell that's in the far field. Okay. So how do we put all this together into a working code? So I'm going to return to this, our domain decomposition. And we're going to break it up into a series of slabs. So these are 1D planes of cells. Typically, we would have a couple hundred or 1,000, but I'm just showing a few here. Now, I said that all the particles initially live on disk, so the first thing we have to do is read the particles off disk and load them into memory. And now we're ready to compute the far field force that we inherited from the previous time step. And we can move one slab down, and while we're doing so, we can be reading another slab. So we have the CPU going, computing the far field force, and the disks going, loading particles. Moving one slab down in this pipeline, we're now ready to compute the near field force on slab 2. The reason we had to wait this long is because we needed to load slab 1 and slab 3 into memory, so we have all the neighbor cells for the near field computation. Now in slab 2, we have the near field and far field force, so that's the total acceleration, so we're ready to kick and drift, which is update velocity and position. Now with the new positions, we can compute multipoles and write out to disk. And that's the whole Abacus pipeline in cartoon form. So the pipeline then moves one slab down and proceeds. So the takeaway is that we actually only need to have a thin slice of the simulation in memory at once. In detail, however, the Abacus pipeline is not actually a pipeline, but instead a flexible set of dependencies operating in an event loop. This is a really flexible way to specify the pipeline because it allows for asynchronous conditions like GPU or I/O or MPI completion. So, for example, the kick, the velocity update, needs to have both force components and needs to have velocities from disk. So the GPU is going to be processing stuff separately, and then when it'll tell you when it's ready. The disk will also be loading stuff independent of the CPU, and it'll tell you when it's ready. So the precondition can incorporate these asynchronous actions, these asynchronous conditions, and then each specifies an action that triggers only when the precondition is ready. Something like the drift might have a much simpler precondition where you just have to have done the kick, done the velocity update. So even though I presented this rolling window picture in the previous colorful slides, that's really sort of an emergent property of the way we specify this event loop of dependencies. So the takeaway from all this, like I said, is that we only need a thin slice of the simulation in memory. It's very computationally efficient because we can overlap CPU, GPU, and I/O, with the CPU handling the far field and GPU handling near field. In terms of accuracy, our typical accuracy is about 10 to the minus 5 fractional error compared to what's probably a few % error in other codes. It's also worth mentioning that the total force is the near field plus the far field, and the near field is exact, full stop, to machine precision. And the far field has just one accuracy parameter, and that's the multiple method. So really, the accuracy of this whole method is controlled by one parameter. The cell size is actually just a computational tuning parameter. It has no impact on accuracy. So this means we're doing way, way fewer approximations than most other codes. So to actually run some of these simulations, I've spent a fair bit of my time in this PhD building computers. So this is Charlie, Franklin, Allen, and Gosling, or maybe Gosling and Allen. They're twins, I can't tell. So because of the unusual requirement that we have a lot of disk per node, per computer, that's what really drives us to build our own computers. So the I/O requirements, I won't go through them in detail, but they're 1,600 megabytes a second is more than a single hard drive can provide. So we stack these big arrays of hard drives. That's what you're seeing in the front here. We combine them in RAID to get the combined performance of many drives. So this cluster is very good at generating heat and noise with a byproduct of m-body gravity, but it's done a lot for our science. So yeah, the reason I mentioned the I/O is because I think it's a good example of the whole Abacus ethos, where we have the mathematical method of the near field and far field split driving a software implementation of this disk buffered slab pipeline, driving hardware design, which is building these computers which have fast arrays of disk. So it's been really fun to work through this whole chain from mathematical methods to hardware design. We have to do everything we can to get the most performance out of our hard drives, especially as the GPUs and CPUs get faster and disks are not getting faster at the same pace. So one of the tricks we play is that we partition our hard drives into two segments. So here's a hard drive with its case off down here. Hard drives consist of a few metallic platters, kind of like little DVDs. And they spin at a constant rate, and they have constant areal bit density. So more bits are passing under the read head along the outer edge than the inner edge. So what we do is we only use the outer half of the hard drives for our performance-intensive storage. And so you can partition the drives into two logical partitions, which actually corresponds to two physical partitions. And indeed, we see about a 20% speed up over just using the whole drive. And we can actually, the inner part of the drive isn't wasted because we have archival data products that we want to store on the inner part. So yeah, this was not my idea, by the way. This was definitely Daniel's idea. But it works, and it's awesome. So I do want to return for a moment to this near field, far field split, because it can seem a little magical, and it did to me for the first many years of my thesis. So previously, I drew this analogy with particle mesh methods where you have the far field leakage, so you can't do exact decomposition. But I want to draw a different comparison now, which is to a tree method or an unstructured method. So let's say we throw out the grid and we just have some unstructured mesh of cells. And we want to ask what is the force on this particle in the white cell here. So we can do a near field, far field decomposition on any unstructured set of cells. We'll just take the closest cells to be in the near field, and the red cells, the distant cells, can be computed with a multiple method. So we can make that choice, and that choice is exact. We're just going cell by cell and making a choice. And then we can do the same for another cell. And proceed for all cells to make some choice. And this is analogous to what you would do in a tree code. So in Abacus, we kind of are doing the same thing, except we're doing so on a structured mesh instead of an unstructured mesh. So the choice that we're making for every cell is the same for its neighbor cells, and it's this structuring of the problem that lets us pose it as a convolution. I think this tree analogy is actually a more accurate analogy than the particle mesh analogy. Okay, so I've talked a lot about the Abacus method. How do we stack up to other codes? So a couple years ago, we participated, or we ran the set of initial conditions from the Euclid code comparison project. So this was a project where a bunch of simulators were given the same set of particles at high redshift to evolve to low redshift. And the point was to compare the answer and make sure everybody gets roughly the same thing. I'll show some physical results in a moment, but in terms of performance numbers, Gadget, well-known CPU-based code, took 34,000 node hours to run this problem. PKDGrav, a GPU-based tree code, took 1,600 node hours, and Abacus took 107 node hours in the basement here. Of course, so this is not a totally fair comparison, I want to be clear, because we had the advantage of newer hardware. It was probably, in terms of raw speed, about 5 times faster than what PKDGrav was running on, but even if you accept that PKDGrav would scale exactly with GPU speed, we would still be 3 times faster and also many times more accurate. This chart here is showing some performance numbers. I won't get into it except to say that we think that we're getting an appreciable fraction of the peak theoretical performance possible from our hardware. So does everybody get the same answer from this canonical set of initial conditions? The answer is not quite. So I'm showing ratio of power spectra here. So power spectrum is a measurement of clustering in simulations. So on the left-hand side is the large-scale clustering. On the right-hand side is the fine-scale, short-scale clustering, sort of the bass notes and the treble notes. And by taking, so if everything were working perfectly, if all the codes agreed, then these ratios would lie exactly at 1 all the way across this range. Instead, you see a scatter in the large-scale regime and divergence in the small-scale regime. The small-scale regime, it's not too surprising given all the different prescriptions that go into different codes for particle softening and so on. The large-scale regime is slightly more worrying because this is actually the regime where we do have analytical predictions for what the answer should be. So which code is getting the right answer over here? It's Abacus. So this is a test of what happens if we run a problem where we have an analytic prediction for the whole simulation for what it should look like. So in detail, this is turning sigma 8 down by a factor of 200. So this is also ratio of power spectra here just on a log scale now. So going up into the shaded region is showing convergence towards zero error. The solid lines are just 2 different redshifts. from Abacus, and we see that on the larger scales we recover the analytic prediction of linear perturbation theory better than 0.01%, compared to the sort of 0.5% scatter from the other codes. So on the right-hand side, we see that we're getting order unity errors. And so what's causing that? So that's actually just due to the finite resolution of the simulation, the finite particle mass. So even if you had a perfect n-body solver, you would still see this overall tilt. And we're confident that that's what's happening is because we have this prediction from this dashed line, which I will actually introduce in the next section how we arrive at a result like this. So this is showing for discrete set of particles versus continuous density fields, what error do you incur on linear perturbation theory. So this plot is actually kind of a nice merger of several of my projects during this PhD. The accuracy and performance show up in the solid lines from Abacus. And the dashed line is a theoretical expectation that we derived during my first project. So I said that Abacus gets the right answer over here. I'm not gonna talk about what's going on over here because that's more complicated and we don't have an analytic prediction for what that should look like. We're thinking about ways to test this though. Okay, so now I want to switch gears slightly and, as I've mentioned, talk about the ways in which the high accuracy of Abacus has let us test initial conditions of linear perturbation theory in detail. So okay, initial conditions are just the positions and velocities you assign to particles at the beginning of the simulation. It's given by analytic theory at high redshift when the universe is nearly homogeneous. And this forms the starting point from which the n-body simulation will take over and evolve the particle distribution. So we have this initial uniform distribution of particles, and we just want to figure out what displacement to assign every particle to reproduce some power spectrum. So we're going to be shuffling all the particles around. They have some velocities too, and that's where the n-body simulation starts. So the standard way in which this is done is the Zeldovich approximation, and it assumes continuum linear theory, which means that you're not assuming you don't think about particles. You think about just continuous density fields, but you're not actually dealing with that. You're dealing with particles. So can we test whether this has any measurable impact? Well, one basic prediction is that the forces on particles are going to be proportional to their displacements. If you test this in n-body code, and as we did with Abacus, you find that this is not true. So you would expect that this particle displaced from here up to here would have a force given by this green arrow in the same direction. Instead, you'll find something like this arrow, and it's not too surprising because this particle has moved pretty close to its neighbor, so its force is going to get deflected. So that's the particle view. The Fourier space view is this spectrum of eigenvalues where plane wave displacements do not yield the same amplitude or direction as continuum linear theory. And the amplitude for any given mode is one of these dots here. So this is the driving of the mode on this axis versus how close you are to the particle spacing. The right-hand side is close to the particle spacing. The left-hand side is large scales. And you see that for any given k, any given mode size, you have a whole spread of eigenvalues, a whole spread of different ways in which the mode can be driven. That corresponds to different orientations of the mode across the grid. So this formalism actually comes from solid-state physics and was ported over to n-body gravity by Marcos et al. And Michael Joyce. And then we realized that this was a very good description of what was happening in Abacus on small scales. So this happens even if you have a perfect n-body solver. And these effects do not go away quickly as you go to low k. They really do not disappear by half of Nyquist or doubling your particle spacing. if everything were working perfectly, all of these values would be either 1 or 0. All this mess down here would just be 0. But you're actually exciting all these transient modes, and that's this whole branch structure down here. So in Abacus, we compute these modes, and actually we initialize our particle distribution to only use the growing modes up here and null out all these transient effects down here. I won't go much more into the detail here, except to say that this is our starting point for a trick we play to compute second-order corrections to initial conditions, which I'll show schematically here because it's a very, very simple idea. So like I said before, one of the predictions of linear theory is that if you displace a particle, given amount, the force is going to be proportional to that displacement. And if you were to flip the particle displacement, you should get an equal and opposite force. So if you were to combine the forces on this particle, you would get 0 force. So that's true in the cartoon I showed here, but if you flip every particle's displacement, that actually breaks the symmetry of the problem. So there's a region of high convergence here, which becomes a region of high divergence here. There's not much happening down here, so the force here is small and the force here is large. So you actually get a residual force component when you add forces from an original and inverted set of initial conditions. And that correction actually is the second-order correction to the initial conditions. So this is how we refine our initial conditions in Abacus, is use our high force accuracy to sum the results of 2 force evaluations on flipped sets of particles to get the second-order correction. Okay, so in summary, what I've said with the initial conditions is that Abacus' accuracy has allowed us to explore ways in which n-body simulations do not reproduce linear perturbation theory, especially on small scales. And that leads to transient effects in the initial conditions and incorrect growth of structure. And we can, and using these insights, we can try to correct for these effects in the initial conditions, and where we cannot correct for them, we can at least understand them. So one thing we've done with these improved simulations is release a suite of 125 simulations. So we launched this simulation campaign on the Elgato GPU cluster at the University of Arizona. Each simulation took a few days on a single node, a single computer. And we ran it for a range of cosmologies, which is shown in this corner plot here. And we publicly released data products through a web portal and with tools to help people download the data and analyze the data. And so this has been this is a valuable public data set for people to use our more accurate n-body simulations. And that's all I'm going to say about that for now. I'm going to talk about one more project that I've worked on during my PhD. And this is thinking about how to reuse simulations in blind challenges. So our motivation here is that n-body simulations are a really valuable tool for predicting what galaxy surveys we'll see, but they're computationally expensive, even with a fast code like Abacus. And in particular, galaxy surveys are probing deeper and deeper regions of space. And the simulations must keep pace. And in fact, they actually must encompass larger volumes than the survey will see. Because you never want your survey to be limited by the volume of your simulations. If you have a simulation box that's only equal to the size of your survey, then you're doomed to declare that your survey is systematics limited, even if the truth is much better than that. So one way in which we want to ensure that galaxy surveys are robust is with blind challenges, in which a simulation team gives an analysis team a simulation they've run without telling them the cosmology with which it was run. They say, analyze this as if it were on sky data. Tell me the cosmology you think it was. and then you can see whether they got the right answer. These simulations must be very high precision because they have to mimic the real universe if you want to have any trust that it will reflect accurate on-sky analysis. And they must be a large volume as well, like I said. And you need to pass many simulations of many cosmologies to the analyzers. And you probably need to do this in many rounds of testing as bugs are fixed and pipelines are refined. So the problem becomes that you can't actually reuse the simulation twice in a blind challenge, because once you've revealed the cosmology of a simulation, an analyzer will just recognize the simulation and say, oh, I know the answer. So we're thinking about ways in which to re-hide the cosmology of a simulation after it's used in a blind challenge. So our hope is that we could use perturbative methods to actually change the background cosmology of a simulation. And we only have to do this to a 0.5% level, which sort of set us on this path of thinking maybe this is possible. So if you run two identical simulations, just changing one parameter by 0.5%, unsurprisingly, the results are going to look pretty similar. And that looks something like this. So this is the original simulation, and then increasing the amplitude of structure by 0.5% leads to this simulation. This is actually just a zoom in of one tiny part of the simulation. So I blink back and forth between these two. They're really similar, and you say, okay, why do we go through the trouble to run both simulations if they're just 0.5% different and really similar? This, I think these, so this is redshift to half. It probably took a couple hundred steps of Abacus, which I think at this resolution would be a day or two. Yeah. So blinking back and forth, you can see that the differences are sort of large scale and coherent. Particles aren't really scrambling up. They're sort of flowing in and out. So we might hope that we could capture some of this effect with perturbation theory. And indeed, if we apply the approximation from the initial conditions to large scales, we can actually sort of get these sort of filamentary inflows. So this is the same region of space, just marking regions of overdensity and our prediction for how they're moving. And you can see we're getting most of the flow right. Okay, so if we actually quantify whether we're doing something good, how does this look? Well, actually not so good. So the target simulation, so I'm showing power spectra in this top panel and then ratio of the power spectra in the bottom panel. The blue line is the original simulation. The dashed line is our target. And the head-scratching thing is that the blue line actually matches the target really well without doing anything. This was kind of surprising to me because a 1% change in this parameter should actually lead to a 2% offset here. And yet we're not seeing that. We're seeing a 0.1% offset. So that's weird. So what we think is actually happening is that the halo bias is evolving even for a 1% change in cosmology. And in detail, these are power spectra of halo catalogs. So the bias is canceling the change in sigma 8. So the punchline is when we actually go to apply this trick of the large scale movement, we overshoot substantially. So we go from this blue line up to this green line. So we're actually worse off than we were before. And you might ask, could we just do nothing and be happy? And no, you don't get quite so lucky in redshift space. There's a systematic tilt. So what went wrong with that? Like I said, the halo bias was evolving too rapidly with cosmology. So we took a different tack, which is to directly measure what the differences are between the catalogs and exactly fit how they are different, and then move halos accordingly. So this looks like this. So this is the large-scale density field in the simulation, and we're turning this density field into a set of displacements that sort of flow along filaments and into regions of high overdensity. And then we let the halos just sort of float down these filaments along these arrows as they like in a k-dependent manner. to exactly fit how the cosmology is changing between two simulations. So when we do that, it works great. So remember, we started out from the blue line, we overshot to the green line, and then applying this additional step of directly fitting what we call a transfer function, we recover this red result, which is exactly on target. They're scattered due to the noise of these simulations, but that's expected. And this is just to show that this brown line here is the redshift space result. It works there as well. But we had to actually run the target cosmology in order to measure the relative displacements, and that's exactly what we're trying to avoid. We're trying to modify the background cosmology of a simulation without actually having to run its counterpart, because if you ran its counterpart, why are you modifying the original one in the first place? So the way that we envision using this is measuring the transfer function between cosmologies. We would run a phase match pair of full n-body simulations, measure transfer function, and then any new realization of the original cosmology can have the same transfer function applied to create a realization of the new cosmology. So just to imagine how this works, consider this Abacus Cosmos suite of simulations, which I flipped through earlier, where we ran 40 cosmologies, all phase matched, so we can measure differences very precisely between them. And then we ran 20 realizations at a single cosmology. So if we measure 40 transfer functions, we can apply each of those 40 to each of those 20 and yield 800 mock catalogs from 40 transfer function measurements. So in summary, we're hoping that this method will help us get the most use out of the n-body simulations that we put a lot of computational effort into making. And so far, it seems to work better than the sample variance of the boxes, meaning that if I gave you a real box and I gave you a box that we modified with this approximate method, you could not tell them apart. OK, so that's what I've done during my thesis. So looking forward, Abacus is exciting because it really enables a whole new class of n-body simulations, I think, where we can really start to answer questions about whether n-body is the right way to simulate large-scale structure and whether it corresponds to what's actually going on in the universe. N-body should converge to this to the true solution for a small dark matter particle, the Vlasov-Poisson solution, in the limit of n going to infinity. But since we usually have fewer than infinity particles, then we'd better check that the errors are acceptable. I'm also really excited right now about deploying Abacus on the Summit supercomputer. Nina Maximova is also leading a lot of this work. The Summit supercomputer is currently the fastest in the world. It has a combination of GPU and memory that's really perfect for Abacus simulations. So we've put in a proposal that we're hoping gets accepted any day now to run a lot of simulations for DESI, a major upcoming galaxy survey. Abacus will also be publicly released, and this will essentially make large-scale n-body cosmology accessible to a departmental budget or a lab budget. You don't need a supercomputer allocation to run massive simulations. If you do get a supercomputer allocation, then you can do even better things. So in summary, I introduced Abacus and talked a little bit about how the mathematical techniques inform a software implementation, which informs a hardware design. It's been a lot of fun to work on this whole pipeline. And the accuracy has put us firmly in the regime where we can study the physics of n-body simulations, and that's what I showed with initial conditions. And similarly, the accuracy lets us perform precision tests of making approximate mock catalogs for blind challenges and reusing these simulations to maximum effect. So large-scale structure is a really powerful probe of cosmology, and accurate numerical modeling is an important part of this. And Abacus is really a small piece of this large puzzle, but one that I hope will help us understand the universe a little bit better. Thank you.
parts have nothing to do with each other. The very beginning you mentioned that dark matter was in there from the start. What evidence do you have that dark matter was really there at the start? That's
BAO.
part one.
Okay. BAO is pretty good evidence. You need some dark component and a light component, a baryonic component that can move against each other. And I'm taking a big risk by describing BAO here with Daniel standing next to me. But I think that's pretty good evidence. I mean, obviously there's famous examples like bullet cluster that show that dark matter is probably some stuff that can move rather than some modification to gravity, if that's what you're getting at.
The second question is, have you tested at all the results for the far field, near field by changing the size of the far field, near field, and everything else constant? Did you do that?
Yeah, so we can change the cell size and the accuracy doesn't move essentially. We can also change the number of cells rather than just the cell size that sets the split far and near field, and that actually does change the accuracy because you're bringing the far field closer to the near field, so the opening angle gets bigger to a given cell. So there, if you do use one cell spacing instead of two cell spacing as we typically do, then you need to crank up your multipole order significantly. But we find that using a two cell spacing is sort of the sweet spot where you're using multiple order 8, which is computationally efficient but not too burdensome in terms of storage.
How reliant is the sort of speed up or the how fast it is compared to other codes reliant on the hardware implementation? Like if I took Abacus and a competitor off the shelf and ran them on an Odyssey GPU node or something sort of typical, is most of that speed up going to be limited by how much you've optimized to the hardware you're using?
No, it's not too optimized to specific hardware in terms of computational speed. So the GPU implementation has been really portable. We've barely had to change aspects of the GPU implementation, porting to many different systems. Actually, the CPU implementation tends to be the less robust part. And porting to Summit, that's actually a PowerPC platform and not an Intel platform, so we spent a lot of time writing AVX assembly instructions that is Intel specific, and then that was not useful in Summit. But we've actually found some pretty nice ways around it where you can phrase the computation in a way that the compiler can generate fast code without manually implementing it in assembly.
So yesterday you mentioned that like a lot of the innovations here you felt ended up being essentially software engineering, which is a line of argument that I'm very amenable to. So I'm kind of wondering, I mean, so there's a tension here where you've delved in very deeply with stuff like AVX 512 and learning how to do all that. And yet now we're graduating with astronomy PhDs. Do you think what kind of training could we provide grad students that would let people be better at this, but also reflect the fact that we're astronomy grad students and not, computer science scientists?
I mean, I learned a lot of this stuff from a combination of some classes I took in undergrad and just tinkering with computers my whole life and just being curious and trying stuff. I mean, it's definitely possible to teach this kind of thing. So not everybody is going to sign up for a Harvard class, of course, but I think it's possible. Seminars are 2-week courses or that sort of thing. Could be held through Wolbach, through the library, to show people, just give people a flavor of how sort of how computers work and how that interacts with software. I don't have any magic bullet, of course. But.
So this is all really great. I mean, it's really great to see the results from what's at least over a decade kind of initiative. But one of the things, just to comment on and highlight and then ask a question, is that I think it's really shown too, like with the initial conditions. Like when you think you also already hit the main points, but it's like, it's amazing to get force accuracy that you can with Abacus, you know, to actually compare numerically, kind of do some of these calculations and machines that we're just not really capable for, like the 12PT and how that can be approached. So it's one of two parts is kind of the question. Either computationally, right, what do you like, or where do you think that the weaknesses of kind of Abacus in this approach are? Is like, so what is the next thing to tackle? Or the flip side, I mean, you also mentioned there's a whole bunch of things of where this opens up, you know, deeper investigations. So either on the science side or the computational side, whatever you want, like what are the real hurdles or the things that you think are the best things to kind of jump at, or something that you're excited about?
Yeah, so in terms of weaknesses of Abacus, the amount of time steps we have to take is definitely the big one. So all particles in Abacus share a time step right now. And so we're wasting a tremendous amount of computational effort doing these beautiful integrations of particle trajectories and voids where they barely move, and you could just get away with 100 steps, and we're instead doing 1,000. So we have a scheme where we give individual time steps to halos instead of particles. Doing it on a particle basis is tricky. And you know, we call that microstepping, but that involves finding halos on the fly. So we can do this, but doing it fast enough is a challenge. So that's kind of exciting, because if we can make it faster, then we can do better physics, which is where I get excited. And the
Yeah, I was just saying, what is the biggest, like, or one of the science driver things that you want to do? Obviously, better physics.
Yeah. So running scale-free simulations is the big push I have in mind in that direction, because that's a kind of simulation where you do have an analytic answer, or you have an analytic prediction across the whole range of structure formation from linear to deeply nonlinear, and we're working on that right now.
Yeah, sorry, this is really cool stuff. So I just wanted to ask guys, so I know you're going to this interdisciplinary Flatiron Institute. Do you have any ideas if you would be able to use the methods that you've implemented in your thesis in other fields that also rely on dead body simulations? Or is this very specialized to cosmological problems? So
I know that electrostatics, a lot of these techniques have actually been borrowed from electrostatics. Even going back to 1985, those particle mesh simulations were borrowed from electrostatics. So, and I think Mark Metchnick and Phil Pinto are collaborators who came up with the original mathematical method for this. I do have plans that I don't know the details, but they are working with that community. In terms of hydro or something else that's really computationally expensive, it's hard because hydro is a local force, and this is all about accelerating long-range forces. But there's definitely improving data products like merger trees and halo catalogs that very much feed into other fields is definitely a way, an interdisciplinary point of interaction.
Well, thanks very much.